surfaces, and historically our main tools are ion beams and electron beams, but we're also using plasmas and photons, and the fields of applications are mentioned here. My work is mainly related to optics and semiconductor industry, because this is used for semiconductor industry. And the final goal, of course, is to bring back to the society something for the money we get. And so we are trying to bring our developments into industry, either via corporations, licensing, or spin-offs. So I'm doing ion beam technologies, and here are some historical remarks. So the first ion beam source, unfortunately, there's only a picture from the back side, dates back to 1973. It's the year when I was born, so there must be some relation. And in the 80s, there was a famous company here in Dresden who built the first full automated ion beam tool, and this was developed based on our work related to ion beam sources. So they built the plant and we brought in our knowledge on ion beam. And when I talk about ion beam technology, so there are two fields: development, either ion beam sources, normally in a circular shape, but here's one in a linear shape. It's about 2 meters in length. We're also developing components which are needed for ion beam techniques, or utilizers or microwave antenna. Of course, if you're developing ion beam sources, you have to measure what these sources have on their performance. So we're developing on our own diagnostics, but we also use commercial ones. And if you develop it, and nowadays in modern times, you're always doing some modeling, some simulations in order to reduce the amount of work which you need to build these ion beam sources, testing that. So if you do a proper simulation, you can see how the ion beam is extracted. So you have here some grids and some potentials. The blue line and the red lines are the ion beams. And of course, you need something to know about the plasma inside the ion beam source. And the second field are processes, applications, and there are two applications. Historically, the most famous one, and still the most famous one, is ion beam etching. So you have an ion beam source directed onto a workpiece, and by changing the ion energy, the ion current, the ion incidence angle, the ion species, you can produce on the surface different effects, smoothing, self-organized nanostructures, and patterning, and so on. And you also can use these ion beam sources in order to remove material for shaping, figuring of the surface. And the other one is ion beam sputtering. So thin film deposition, so you use an ion beam source, sputter some target material which condense on the substrate, and the film is forming. This is not our main goal in film deposition. We are basically interested in the fundamentals. So what is really going on in this process, what comes out, and this is what I'm talking today about. And I will show you some applications related to some film deposition. Here are some examples. So ion beam etching, you have these self-organized nanostructures. Here you have a smooth surface, and this is done with the same process, just by changing rotation of the sample and by changing the ion incidence angle. Then we have here some kind of a grading, and if you, I don't have it here, but here I have a grading. Can't see it in AFM, that's why you do this autocorrelation. So here the size is less than 0.5 nanometer in height, but it's still a grading. So you see it here, autocorrelation is much better. Or here's a surface, this is a mirror, a large scale mirror, Serrador, 80 by 150 millimeters, and this is the offset from the target shape of the surface. And by ion beam etching, you can reduce the offset from the target shape by a number of 50. Let's go here, and here's some ion beam sputtering. So we have here some thin films. You know it much better than me. You did probably much better pictures and multi-layer coating. And we are, as I said, mainly related to fundamental processes. So you have here the sputtering field, the number of sputtered atoms per incident ion, independence on the ion incidence angle for different ion energies. And this is what we want to know, because this helps us to understand if ions unwanted hit some of our objects. And now we want to see how these objects erode, how fast, and then we need these parameters as input parameters for modeling, and we can also say that this is the reason for this erosion we do not want. So come back to the topic. I missed here sputtering. I could say I skipped it because the picture is here, but it was not on purpose. So as I said, we have ion beam etching and ion beam sputtering. So we have always an ion source, and the effect is different. So here you want to remove material in order to shape the surface. Here you want to remove material in order to draw a film or to study what is going off. And all this is based on ion-solid interactions. A nice picture. So you have an incident ion, and somewhere another particle is emitted from the surface. And in a smaller and more realistic picture, it looks like that. You have a primary ion beam. Here some collision cascade evolves, and by momentum and energy transfer, somehow sputtered particles leave the target, and also scattered primary particles leave the target. And what are you interested in? First of all, the primary particles. You need the current density profile. You need some kind of information about the beam divergence. You need to know what ions come out. If you use argon or xenon, then you know they come argon or xenon, but if you make complex chemical compounds, then there are different species. You have to know the ion energy in the start charge state, and you also have to know something about the secondary particles, so the angular distribution, the angular dependent particle species and particle energy. And this brings me to what we are talking today about energy selective mass spectrometry. So these species or these properties can be measured with energy selective mass spectrometry. And these properties, and this is what I'm talking today, and the next talk is given by Krokam, and he will talk about more about the primary ion beam. And yes, so we have ion beam sputtering, just a small sketch in order to bring you to the point what is really important in this talk. So you have an ion beam source which hits the target at a certain incidence angle, and if you select a certain direction, you can specify the polar emission angle and the scattering angle. So the sum is always 180, and you can of course look at different angles, and this is what we are doing in our experimental setup. We have here a semicircular target holder, so we can place a target each step 10 degrees. And so simultaneously with one experiment hitting the target, we can have several samples for different emission angles and scattering angles. But we can also flip the target around, take this holder off, move the ion beam source, and then we can use an energy selective mass spectrometer in order to make angular dependent measurements of the energy distributions and mass distributions and so on. So we have two things, thin film curve particle characterization combined in one chamber. So it's the first time that we can do now correlate particle properties with thin film properties. So why is this important? If we're talking about thin film deposition, then we always know, everybody knows, films depend, or the properties of the films depend on the technique you are using, and not only on the technique, sometimes also very much on the process parameters of the certain technique. So if you want to have nice films, you have to understand the particle properties and how they are correlated with the process parameters. So this is a generalization which holds for every It's deposition technique, so if you want to have very good films, you have to know what you are doing. So the main part is about particle properties, and I start with the energy distribution of spot of particles. So we have here the count rate in versus the energy, and from top to bottom we change the scattering angle. So if we go back, so we are going this way. Scattering, looking this way, scattering angle goes longer, and this is what you see. And there are two zones. The zone here for the scattering angle larger than 90 degrees, you have a so-called Thomson-like shape. Thomson predicts a shape of the spot of particles independent of the ion energy and so on. So it's just a low energy peak and a power law decay. And here you have not much variation, but if you go to smaller scattering angles, here some structure evolves. And yes, it's not really easy to see, but it's a very broad peak. And so the tail is not power law decay-like anymore. And we extend this, or we assign this effect to so-called anisotropy effects. That means that the sputter target particles are not from the collision cascade, but rather from a single or few collisions. And this is supported by this simple question. This is physics first semester, so two-particle elastic, two-particle interaction, and you can have these experiments. I have the incident ion, you have a target particle, this gets scattered, and the energy is given by this relation. So you have the scattering angle and the mass, and the incident ion energy. And if you calculate here the energy of the target particles with this relation, it depends on gamma, you get something like this curve. And this, for me, is quite well describing what we see here. So what happens if you have argon and silver, you have xenon and silver, the same experiments, the same curves, and what you see basically is the same. Okay, the tail extends a bit more to higher energies, but the shape is principally the same. Now we can also change the ion energy. So you have here the same curves as here. Now in one picture, 1000 electron volts, 30 degrees incidence angle. If you increase the ion energy, you get the same shape, but the curves, the tail, not the maximum, the low energy max, but the tail extends to higher energy, and this fits to our formula because the target particle energy should scale with the ion energy. Or if we have here on this side change the ion incidence angle, so the ion energy is the same, but the incidence angle is increased. Now we have the emission angle. Please note, the colors do not correspond to the same emission angle, but to the same scattering angle. And if you do that, so same color for same scattering angle, you see that the shape of the curves is almost the same. That means the shape of the curves is driven by the ion energy and by the scattering angle, and this is what corresponds to the similar formula. Now we go to the scattered primary particles, argon and silver, so we're looking now at the scattered